Hi everyone, I'm Phil Nash, developer advocate at JetBrains, and I'm going to give you a tour of some tips and tricks in CLion in the context of competitive coding challenges. Now, I should confess up front, I'm not a competitive coder myself, but I do know C++ and I do know CLion, so I hope there's plenty you're going to get out of this. With that in mind, I'm going to work through an example of a typical coding challenge and see how CLion can help us through it all. So here's a new CLion project. Just been created, so has a default hello world sample, and there's just one other file that I've already added here, and that's this markdown file containing the problem description. If I open that and close the raw view, we get to read the description in markdown rendered as nice HTML. Now, this is based on a problem I found on one of the common competitive programming sites, but I've reworded it a bit and changed the examples, so it's not an exact copy. But it's a fairly simple challenge. Purpose here is to get a feel for what CLion can help with, rather than getting too distracted by the problem itself. So, write a function that finds the longest common prefix string amongst a vector of strings. No common prefix is found, return an empty string. So far so good. But then got some examples here to verify, and some constraints down here at the bottom. Now, I think the main thing to note here is that both the vector itself and the strings inside it can be empty. They'll also never get very big, which may or may not be useful to know, and the bit about just lowercase English characters, sometimes that can be useful as well. Okay, let's get started with the problem. Now, going back to main, we could actually just start from here, just write our code directly in main, visually verifying from the command line maybe, or in the debugger, or perhaps using asserts. But personally, as an advocate for testing and TDD, I prefer to use a test framework, even for this. Now, as I said, I'm not a competitive programmer. You may disagree that that's the best approach, but I do know some in the competitive programming community that do this. It's not just me. So while that's not the purpose of this talk, if you are skeptical, do keep an open mind, watch how it works out. Right, now, certainly we don't want to waste a lot of time getting set up with a test framework. Fortunately, the framework that I originally got started, Catch, now Catch 2, comes in a single header. So if you've already got it lying around, it's quick and easy to get going with. So I've got it just off screen here, copied it onto the clipboard, I'm going to paste it straight into CLion's folder view here, and you can see it's going to copy it in and even let me rename it if I wanted. I'm not going to do that. Now, if you've used Catch 2 before, you'll know that to avoid long compile times, which is really going to kill us, waiting for the whole framework to build every time, what we want to do is just have one source file. We'll use this one, where we first of all include the catch header, and then just before that we hash define catch config main. We'll just do that in that one file, and at this point we can start compiling. It's going to take 10 seconds or so, so let's get that out of the way while we'll go and add another source file. Now, here we've got the option of adding a class, which will take care of a lot of boilerplate for us if we need that, but we probably don't need a class. There's certainly not a whole file for it. We just want a simple C++ source file. So do make sure you select this one though, rather than the even more generic file. Otherwise, it's not going to be automatically added to the CMake file. Now, for our purposes, we probably don't want an associated header. We could have that if we wanted, but we do want it in the CMake target. That's going to save us a bit of time, so leave that checked. Now, this file needs to include the catch header too, so we'll do that. And notice that they're doing this, it's just a couple of keystrokes with CLion's completions. So it's not taken very long to get up and running. And in fact, even opening a Catch 2 test case gets suggested after just a single keystroke here. So we haven't wasted a lot of time on this, and we're already ready to get started. Now at this point, I would usually talk about good test naming, but I don't think that's a concern for us here. In fact, we don't even have to give you one, so let's skip that. And at that point, we are ready to start. Let's go and have a look at our test inputs. So if I open the problem statement file again, and I'm going to split and move down so that I can see them both on screen at once. Now these arrays here, they're in pseudocode. This is not the notation that we can use in C++. So I'm just going to grab the strings themselves out, and we're going to pass them into a function. Up here we're going to write called LCP for longest common prefix, and we'll pass them in as a direct array or initializer list constructor, and then compare that, the result of that, against our expected output, again from our problem description. Now we're missing a few things here, of course, including the actual function, the LCP function. We haven't written that yet. Now this is classic TDD. Now I'm not recommending you use strict full TDD here, but actually some of the techniques and principles do still help us. So that's what I want to watch out for. So by writing the calling code first, the test first approach, it does actually give us a better idea of what our function needs to look like. So that's why we've done it that way around. But now we actually want to go and write the function. So before we do that, again, I wouldn't do this in production code, but I know here it's common practice. So we're going to, using namespace std, so we don't have to do std : everywhere. And now we know we need to return a string. The function name is LCP, and it takes a vector of strings, or maybe even string views. I would actually use string views here. And in fact, I'm going to even return string views. Now it's common to receive these vectors as non-const references in one of these coding challenges. And sometimes you can use that to your advantage by mutating the inputs in place without additional copies. But we don't know if we're going to need that yet or not, so I prefer to start out with a const ref, because that's also going to make the calling code simpler. We can just leave those temporary initializer list constructors there. And then we'll change that later if we really need to. And finally, to get the function just to compile, it's another TDD trick, just return the simplest value. We're not looking to pass the test here, just to get it to compile, just so that we can see it running end to end. And in this case, that's going to be an empty string. So we can now compile that already, and it does compile. Not going to run it because we're not actually put any tests in even yet. So before we do that, let's grab the next example. Now, so we're not testing anything just yet. What I want to do is capture all the examples up front with the least amount of code for now. Now, we've only had those two examples from the problem description, but given what we know about the constraints, I'm going to have a couple more, because we know we're going to need to handle the empty vector case. And there may be a special case around a single item as well. So we're going to add that one as a separate test. So we've got 4 tests now. You might want to add some more. I can certainly think of some others to tease out some different edge cases, but we're going to go with that for now. And we're finished with our markdown page. I'm going to close that to give us some more room. Now, obviously we can run that at this point and nothing gets tested because we don't have any test assertions. So let's add them all quickly by using column selection mode to give us multiple cursors. So we'll use catch's check macro, because that will continue even on a failure, so we can see how many things fail and what they fail with. And now we see some results. Now there's only 2 failures because 2 of our tests were testing for the empty string, which is what we were returning anyway. If we want to force that, then we can just put something else in the return value for now, just to see them all failing. Might be worth doing that. Again, it's a TDD technique. You may or may not want to adopt it. But I mean, do notice that our compile and run turnaround is pretty fast. So getting that speed is part of the secret of TDD, but it really serves us well here as well. And now we know that we're testing what we think we're testing. So that's an advantage. And by the way, if you are using Catch 2, you can also use the integrated test runner, just by adding a run configuration for it. Now I'm going to use the constant output here because it shows the count of failed assertions, which is going to be better for our usage, but experiment and see what works best for you. Enough talk, let's start implementing our function. So again, steering close to TDD principles, let's get those simpler edge cases out of the way first, because sometimes that can simplify things later. So empty container, that one's easy enough. What about a single item? So it's easy enough to get that one out of the way as well, but maybe that will drop out of the algorithm once we've developed it. Maybe it won't. So we'll come back and look at that again afterwards. But for the rest, we're obviously going to need to loop over the strings at some point. So we'll probably reach for a for loop. Now, notice I get some completion options here. Now, if I accepted indexed for, I get a live template with an integer index, and that can be useful. But if I just want each string, maybe I don't want to do it that way. So let's have a look at what's available. If we go into the settings and search for live templates, under C++, you can see a few options. Now, the last one there is one that I've added, and we'll look at how you can add your own later, and we'll also see that one in action sooner. But the first three there are bundled with CLion, and they're all to do with for loops. So we've seen the first one already. Next one we have is iter for range-based for loops, and then it for iterator-based loops. So we could go for the range-based for loop here and get every string. But I think what we really want is to compare the first string with every other string. So we're going to want to skip the first one in the loop. And that means we're going to go for either index-based or iterator-based. Let's go with the iterators. So it is. So I'll shorten the suggested iterator name here. And then we just need to start from the second string. And we're about done. Now we know that that's safe because we've got a random access iterator, and we know that there's at least one item in the vector at this point. Okay, so we need to see at what point this string diverges from the first string. And there's a standard algorithm for that, mismatch. Now if we let that complete, we can see all of the signatures. And the form we want will take two iterator pairs. We're not going to be needing to supply a predicate. Now dealing with iterators is still a bit more tedious than it could be in C++. When ranges fully takes over, that's going to get easier, but for now, at least CLion will help us with all the completions, so it's not so onerous. Now, I can see that strs0 coming up again and again. Let's extract that as a variable. Replace all three usages so far, and I'm going to call it S1. Looking a bit nicer. Now let's finish our call to mismatch, and fortunately we're still sitting there. So now we've made our call, we can hover over mismatch and see the full signature. We can see that it returns a pair of iterators. And we can probably guess, even without looking it up, that that's going to be the iterator for each string at the point at which they diverge. And that's exactly what it is. So let's catch that result. Now for either of those, we can get the common prefix length using stood distance. We'll go with S1. Now we need to track these across all strings, so we're going to need a variable outside the loop. But what type should that be? We hover over our prefix length variable, we can see that it's been deduced as a long. So let's declare a variable to track the max prefix length up here, and we're going to update that in the loop. Now, after the loop, we can use that to return the actual prefix. Okay, let's see what that gives us. Well, we got one failure. We got too long of a prefix, and you probably already spotted it as I wrote it. The mistake I made, it's the minimum common prefix we want, not the maximum. Easy mistake to make, but easy enough to change. Just need to change our std max call to std min. Trouble is now that variable name is very wrong, and we've used it in 4 places. But changing that everywhere is just as easy with the rename refactoring. So now running that again, still not quite right. Now there's no prefix. And that's because now we need to start at the other end of the string, not at 0. And that does it. All our tests pass. Now this might be a good time to add more test cases, but it could also be a good time to take a look back, see what we've got, and see if there's any opportunities to optimize. So we've got lots of begin and end calls in the loop. I might be tempted to factor these out too, but I'm fairly sure that they're going to boil down to optimal code even as they are, so I'm going to leave them as they are. But thinking about the point we get the current common prefix, if we get a 0 here, we know that we're not going to be able to get any lower than that, so we can shortcut the loop and avoid looking at the rest of the strings because that's not going to do us any good anyway. So run again, the tests still pass, but are we actually hitting that case? We're not really doing TDD, so we have less confidence in that. So let's just add a breakpoint there and find out. Well, our breakpoint is hit, so yep, that's it. And if we look up the stack, we can see that it's our set of strings that have no common prefix, so that's not very surprising. Everything is as we expect, that's good. And finally, we can see that our algorithm handles the single string case, after all, because we're going to get the full size of the first and only string, skip the loop, and then return that as the substring. So let's remove that special case line, retest, all still works, that's great. So maybe you can find some more things to optimize here. That's about as far as I can take it. But there could be some other approaches we could take. So if you want to have several attempts at the same problem, you probably won't want to throw away the previous attempts. There's a few things that you can do here. Each will have their own advantages. First, you could block comment the code out. Bit of a blunt instrument, but it works. It's familiar, quick and easy to do. Personally, I prefer to push all of the code into a namespace, so I can easily switch between them, and it continues to compile. Now, that's where that live template that I created comes in. If I bring up live templates here, so you can see it there. I can even get to it with this shortcut. Now, because it's a surrounds with template, it's going to wrap all the highlighted code and indent it properly, just in one step. So that's what we're going to do here, but I'm also going to mention a third approach, which is just delete the code, because we can still get back to it at any time with local history. Now, local history works just like an automatic local version control. Every time you compile, save, or perform a refactoring or some other action that changes the code, you get like an automatic check-in to this local history. You can see the diffs go back to any point in time. You can even see test results in there. So we're going to stick to the namespace approach, go back to the code. I might copy some of it out to start my next attempt. Now, this time, I think we'll start with the index-based loop, but this time it's going to be over the string instead of the container, that first string. But then I'll grab the iteration over the rest of the strings again from above, so it's handy to still have that there, although it's so quick to write with the live template. Wouldn't have been that bad anyway. Now we want to compare the indexed character, but only if we're not off the end of the string yet. So we need to test that first. If we are at the end of the string, or if the indexed character differs from our first string, then our prefix must be whatever we got up to here. So let's return the substring at this point. But if we get to the end of the loop without any early return, then our first string must be the longest common prefix, so we'll return that. Now we don't have a test for that specific case other than the single string version, so we might want to add one just to be sure. And we're done. So looking for optimization opportunities then, we can see that this strs.begin +1 is redundantly recomputed for every character. Now, good optimizing compiler should still be able to spot that and hoist it out of the loop for us, but just to be sure, we might want to extract that as a variable ourselves, since it is so easy to do here. And I think that's as far as we'll go with this problem. I just want to go back and look at some things in a bit more detail though. So first, for some of the refactorings that I did, I needed to select a particular expression. And while you can do that just with the cursor keys or the mouse, if you're already positioned somewhere in the expression, you can expand the selection to increasing scopes with just a single shortcut, and of course bring it back down if you want to. And then once you've got what you need, you can see all your refactoring options from this context menu here. Now, of course, it's best to learn the shortcuts to be able to use them most rapidly. And these are some of the easier to remember shortcuts mostly. But if you do forget, or if you're trying to learn them in the first place or just see what's available, this is a great place to go. So having a look through, rename and extract variable. Well, we saw those a few times. And they're probably the most useful refactorings overall. Now, extract constant is just like extract variable, but it extracts to a global or static constant instead. For extract method, it extracts the selected code into a function or method. And while you might use this one less, it does more work for you if you do need it, because it works out what all the arguments need to be passed in and all their types. It can be a bit tedious otherwise. Now, all of these extractions can be reversed back again with inline, another refactoring. And then we have extract parameter. Again, like extract variable, this extracts the expression out, but in this case to the caller, passing it in as a parameter. So this can do quite a lot of work for you again, especially if there are lots of callers. And you can also extract hash defines and type defs, and there's a few more refactorings to do with classes and class hierarchies that we won't talk about so much. So it's worth learning and becoming familiar with all of these, but particularly in that order of usefulness. So if nothing else, just remember extract variable and rename. Now, we also used a few live templates. Now there's two types. The plain ones can be triggered just by typing their abbreviation and using completions, like we did with the for loops. But for surrounds with templates, you need to select the code to surround and then hit the shortcut to bring up this list. The first few are built in, and then there are any that you added as live templates, like my namespace template. And from here, you can also jump straight to the page in settings where we can set them up. So let's have a look there. So these are the four that we saw earlier. But looking at the bottom, we see where we can specify the abbreviation for triggering them, the description that gets displayed in the completion list, and then the template itself. And templates can have variables enclosed in these dollar symbols. These can be just placeholders, or some have special meanings. So end here is where the caret ends up at the end of the instantiation. If it's a surrounds with template, like NS, it will have selection instead, and that's where the selected text will be inserted. But for the other meanings, we need to look in the Edit Variables dialog. Now here we can map variables to expressions or default values. Expressions can include literals, other variables, or special functions. And these functions are quite comprehensive. Some are quite sophisticated, like the right side type, used here to get the type for the iterator. Functions are fully documented in the template variables page of the CLion docs, and it's well worth having a look through there to see what it can do for you. Now, another whole set of features that makes CLion particularly powerful is its search and navigation features. Find in path, for example, has an easy-to-remember shortcut and gives you results instantly, similar for replacing path. But CLion really comes into its own when you apply its understanding of the structure of your code too. And this is the easiest of all shortcuts, Shift-Shift on all platforms. Now we can see search results broken down by class names, file names, symbols like variables or functions, and perhaps the most useful for competitive coders is Find Action. That's the last tab in Search Everywhere, but it also has its own shortcut. And here we can find any action that CLion can perform. For example, Find Action itself. We can invoke that action from here, or just check its shortcut or menu path. You can even assign shortcuts straight from here, which is especially useful if you often use something like local history that doesn't have a shortcut by default. So if you only remember one shortcut in all of CLion, Find Action will take you to all of the rest. So thanks for watching and enjoy competitive programming with CLion.